Thanks for joining us. Welcome to another episode of Imaging Nation, a podcast brought to you by the Biomedical Engineering and Imaging Institute here at the Icahn School of Medicine in New York City. Today, we're really excited to be having a special guest, Dr. Hung Yeo, who we're going to introduce in a second. But first, I just also wanted to introduce our co-host for this episode, Mallory Stellato. Mallory is a recent team member added to the BIMI family, and she's been absolutely killing it thus far, super quick, and has already improved pretty much all of the communications and media efforts that we make here at the Institute. So, hey, Mallory, thank you so much for joining.
Hi, Jazz. Thank you so much for that very kind introduction. So I'm Mallory Stellato, and I recently joined BIMI as a program manager. My background is in public health, so I hope to bring that perspective to this podcast. Thanks for having me.
Yeah, so Mallory and I actually were really excited to find out a little bit of a fun fact. We both went to the same college, a few different years apart, but the same college and did the same major. It was a major called Biology and Society. We both went to Cornell in like upstate New York in Ithaca. And BSOC specifically, the major kind of blends considerations of bioethics and system level looking at the health system overall. Kind of all complemented by true hard science and biology, organic chemistry, all that fun stuff. So it's cool we both share that background a bit.
Yeah, absolutely. I think it's also, such a nice foundation to bring into a place like BIMI, which is so interdisciplinary and so much about translating science and engineering into real life applications in medicine and beyond. So I think we have a good foundation to talk about these concepts.
Totally. And hopefully it doesn't make us too precocious if we start to branch into a little bit of ethical quandary and discussion later on in this podcast, because today's guest is really someone who is pushing research, who is truly at the forefront of what could be incredibly cool, but also has a lot of considerations into how we interact with technology in a clinical and in a consumer way.
Absolutely. Yeah. I think when you're talking about sort of human computer interfaces, people are going to naturally have questions about ethics and some of the safety and security behind that. So let's get into it.
Totally. We'll have plenty of time to pontificate. So we will now introduce Dr. Yeo.
So Dr. Hung Yeo is an assistant professor in the George W. Woodruff School of Mechanical Engineering and Wallace H. Coulter Department of Biomedical Engineering, and the director for the Center of the Human-Centric Interfaces and Engineering at Georgia Tech. Dr. Yeo has established a strong research program in fields of nanomembrane electronics and human-machine interfaces. We're excited to hear about that because from the get-go it sounds quite confusing. Dr. Yeo, just a little bit of a background of his education. Dr. Yeo received his PhD in mechanical engineering at the University of Washington, Seattle in 2011. And then from 2011 to 2013, he worked as a postdoc research fellow at the Beckman Institute and Frederick Seitz Material Research Center at the University of Illinois at Urbana-Champaign. Dr. Yeo has also published over 80 peer-reviewed journal papers and has received a total of $6.5 million in research grants from various agencies, including just some of the small ones, the NIH, the DoD, the NSF, and the AHA. So we are extremely grateful that he took the time out of his very busy schedule in order to sit down with us today and talk a little bit about the future of soft electronics and bioengineering, specifically in biosensor design. So Dr. Yeo, thank you.
Thank you. Thanks for having me here. It's my great pleasure to be here and talk about my research.
Absolutely. Maybe we'll dive right in because there were a lot of phrases thrown around in that introduction, which are extremely exciting and also a bit unfamiliar to, I think, most of our ears. So would you kind of start off by, I guess in your own words, explain your research, explain your lab?
Yeah, sure. My lab here at Georgia Tech, so as a team, we are studying a few different things in terms of engineering aspects. So we study materials and mechanics, fabrication, and machine learning, something that you are hearing these days, and system packaging, and so on. So multiple areas of fundamental science, and we use those knowledge to develop new systems. So that's something that I'm going to talk today. We call it as soft electronics. because it's made of different materials, something that you cannot see in real world. So we are trying to use very soft, deformable material to develop new sensors, so that you can use those sensors for wearable applications and implantable applications, and also human-machine interfaces.
That's awesome. That's incredible. So would you break down, so you talk about some of the material differences, but if you could kind of sum it up between, I guess, soft electronics, is it fair to say hard electronics is the opposite? What's the delineation in that field?
Exactly. So the electronic systems that we see and we use on a daily basis are made of rigid materials and hard materials. So your cell phone, your smartwatches, laptops, tablets, they are rigid, right? So you cannot really bend it. Even though these days you see there's a smartphone that's foldable, but it's still rigid because of materials, right? We use that metals and plastics, semiconductors are all made of rigid and hard materials. So we call it as hard or rigid electronics. But here I'm developing new electronics that's made of completely different materials. Now it's very soft, like our human skin. That's really easy to understand, right? So we make sensors and electronics based on materials like human skin or internal organs. So it's very soft, flexible, stretchable, squeezy, stuff like that. So we are trying to follow the human tissues, mechanical and material properties, so that you can have better matching between our target tissues and sensors and electronics. So that's the major difference between our soft electronics compared to the conventional rigid electronics.
Wow, that's super interesting. So can you tell us what the advantage of using soft bioelectronics is compared to these more rigid ones?
Yes, that's a good question. So first of all, in terms of form factor, in terms of size, dimensions, soft electronics has exceptionally smaller form factor compared to rigid electronics, because we use very thin materials instead of thick, rigid materials. So we can make it very thin, and you can shrink the entire size of sensors and circuits at the same time. So that's the biggest advantage of soft electronics. And at the same time, the materials for soft electronics are following, again, as I mentioned, the mechanical and material properties of the target tissues like human skins. So it has better skin compatibility. In other words, like biocompatibility, because it looks like our skin. So it's more safe, right? It's safe and is having better contact to the skin. So that's another advantage, that we can keep these sensors and electronics on the skin or inside the body longer than the conventional rigid electronics. And also, as I mentioned, that we can shrink the entire size. At the same time, we can lower the weight, right? So it's going to be ultra light, at the same time ultra thin. So it can have a lot less or pretty much negligible mechanical burdens to the user. So when you hold your smartphone, it's heavy, right? However, once you make this soft electronic based smartphone, it's going to be less than 10 grams, including battery. So that can give you pretty much no feeling when you're holding this electronics. So basically we can use these devices longer than the previous electronic systems.
Yeah, and maybe this is a good way to, because obviously this technology can have huge impact in both clinical settings and like consumer electronics. I mean, I remember when the foldable displays came out at the Consumer Electronics Show a few years ago, and everyone went crazy, oh my God, it's the future. And then it kind of seemed that all we really saw out of that was Samsung's curved display. But I guess we should probably stick a little clinical right now. And it seemed that a lot of the research that you were putting out, a lot of the videos that we can find on your website, which we'll link in the description because there's a ton of great information on that, and the wide breadth of research that you're doing. It seems like a lot of it has to do with muscle recording, with on-skin recording of muscle signals signaling to then control some kind of prosthesis, some program, some wheelchair, some something. So how would you say that having these foldable, these kind of more malleable materials allows you to conform to parts of the human body which maybe before weren't accessible by electronic sensors?
Yeah, that's a good question. So, you brought that muscle recording, right, with sensors. The conventional devices, or something that we have at the moment, can measure those signals, which is called electromyograms, right, muscle activities. It's something you can measure on the skin. It's possible to measure those signals with existing sensors. However, as I mentioned before, that the existing sensors are made of rigid materials. But when you think about that, putting that rigid materials on the skin is compatible, soft and biocompatible and stretchable, things like that. There is an air gap, because of the materials differences. So, because of air gap, we have to use other materials like conductive gels made of sodium-like materials, things like that, to cover those gaps, and then we have to basically press the sensors to the skin as hard as we can, so that we can maintain that data recording quality. So there are a lot of issues because of those arrangements. First of all, it's not comfortable. Second of all, that gel that we have to use can cause skin side effects, right? Irritation, allergic reactions, and so on. And also, you have to push your electrode to the skin, which obviously is not ideal to wear it more than multiple hours or multiple days or things like that. So here we are using soft sensors, right? Instead of these rigid materials. Then now we can remove all those issues that I mentioned. Now it's very thin, so it's less than 100 micrometers. We make sensors within 50 nanometers, which is 1,000 times thinner than single human hair.
Wow.
So compared to that rigid electronics, now the soft sensor can make really good contact to the skin. Okay, so it's just another skin layer on top of your skin. So we don't need any other gels or aggressive tapes, adhesive, stuff like that. So we can have natural conformal contact between sensor and the skin. So that arrangement can remove all those issues that I mentioned earlier. At the same time, it can offer better signal quality. And also, because of those advantages, now we can measure high quality muscle activities for a long time, not just a few hours. We can wear it more than a few days or a few weeks.
Gotcha. So future clinical tech that you would see this being applied to, will people be able to is this a lot of adhesive-based things? Will people be able to take this on and off at their comfort for kind of long-term signal recording, maybe if they're, using it as a diagnostic tool? What's kind of the level of permanence that these technologies, you see them integrating in these clinical outlooks?
So I guess it's pretty much unlimited. This new technology can be used for many different areas of clinical work, including, as we mentioned, that we can definitely use this device for better diagnostics systems, right? And also we can use this device for advanced therapeutics compared to existing systems, because typically we have to be at the hospital with big rigid gadgets and other apparatus and things like that, but we can shrink those things down to in a way that we can wear those devices so that we can do those therapeutics even at home. At the same time, we can use these devices for rehabilitation and controlling prosthesis, something that you mentioned before. So many other things that, obviously I'm not a clinician, so I cannot imagine all those applications. However, I can definitely see that our technology can be used in multiple domains.
Right, that's really exciting. So I guess that leads me to wondering which types of patient populations are you working with, and what types of medical conditions are these soft bioelectronics best suited for?
Yeah, good question. So currently we have more than 10 projects that require the development of new biosensors and bioelectronics.
That's unbelievable.
Yeah,
And I
so
imagine there's only
great.
hundreds more that it could be applied to in your noggin right now.
Yeah, it's just the
Yeah,
beginning.
Yeah, I'm not getting 100 projects at the moment, but so yeah, I have those projects where we can use our new systems for diagnosis and others. So one example that I can tell you is that currently we are working with Emory Medicine here in Atlanta with cardiology. So we are targeting to develop new biomedical systems that can measure a patient's heart activities, which is called electrocardiograms. That's something you can measure on the skin by using sensors. So instead of using the conventional electronics that can be wearable less than 24 hours or things like that, now we are trying to develop multi-week long data recording systems. Even they can do that at home. At the same time, this device, soft electronic systems, can also have the AI capability, the artificial intelligence capability, something that you are hearing these days, right? So that capability can offer smart diagnosis, real-time onset diagnosis. So basically, the machine learning algorithm, which is embedded in the soft electronics, can tell you whether you have any abnormal signals in terms of cardiac activities. So let's say, for example, you are getting like heart attack type of signals or arrhythmia, atrial fibrillation, things like that. Then our system can measure it, and then we can alert it to the user. At the same time, we can send those data to a clinician so that they can download it or open the data immediately, so that they can do immediate actions for that patient. So that's one example.
Really quick, if you wouldn't mind me just asking a bit more questions about that, because I remember when the Apple Watch came out, the Series 3, and everyone was going, or it might have been Series 4 when the EKG was first released with it, and it was a ton of excitement because that ability to have kind of control over your own biomonitoring, I think, is inherently very exciting, but specifically in regards to the AI aspect and to getting types of alerts and preclinical diagnoses off of those EKG readings, there were some concerns and considerations about. I mean, for example, if I'm watching a particularly exciting episode of Survivor or something of the sort, and my heart rate soars above 120 BPM, my Apple Watch will go, "You're sitting down, and that's above that. Something doesn't seem quite right." Obviously, that's more of a funny anecdote, but how are you kind of, or what do you see that the interplay between the AI and being too much of a diagnostic tool leading to, I guess, some patient fear?
Good question. First of all, your heartbeat, that warning is not correct because it's only measuring the single parameter. So as you mentioned, that's very important to avoid any unnecessary fear, right? So we have to use multiple sensors, not just single sensor, because single sensor can give you wrong information.
Right.
And on top of it, first of all, the signal that you are measuring by using Apple Watch, I'm not criticizing Apple Watch, but that Apple Watch recording is not 100% accurate because it requires very close contact of sensors to the skin. So basically, you have to really tight your wristband to get correct recording. However, if there's any air gap or there's loosened contact, then the data that you are getting is not correct. So that's why it can give you wrong information. So
that sounds like a fitting issue, not necessarily the tech issue.
Exactly, it's not just about sensors.
Right.
But that's one of those requirements to get accurate recording. But it's not really easy because basically you have to strap yourself and block your blood flowing. So that's why we need a better sensor, right? A better sensor meaning it should be better in terms of wearability, but at the same time the accuracy. So here, what I'm trying to do is to replace the single sensor configurations, trying to have multiple sensors in a single device platform. So in terms of size, it's pretty much same as Apple Watch. However, it has multiple sensors so that we can have the combination of data recording to see whether one sensor parameter is correct or not. So we can use that AI to see what happens between those measured data to give you better diagnosis. And obviously, healthy people do not need to use this device on a daily basis. However, we can make this device usable for patients who need continuous monitoring so that you can have continuous real-time data analysis and diagnosis for somebody who really needs to be monitored. So there are multiple ways to play with this device. However, as I mentioned, that accuracy is very important, and to have good accuracy, you need multiple sensors and better sensors.
Mm.
Yeah, absolutely. This is so fascinating. So I'm also wondering what was sort of your aha moment or spark that led you to this field and kind of brought up all these very futuristic sounding ideas?
Yeah, that's a very good question. There are multiple, occasions that I had during my career. But first of all, I got into this, biomedical field as a mechanical engineer. That's what I studied. Yeah, it's a sad story, but I'm okay right now. But my father passed away when I was 21, all of a sudden during sleep. And he was diagnosed as myocardial infarction. And we never knew that. And he had no symptoms at all. So he had zero symptoms, anything like that, but suddenly he died during sleep. And so I studied that field, and I found out that even though our technology is rapidly developing, there's still big gap between new technologies in engineering and biomedicine field, because it's not necessary for clinicians to adapt that new technology right away. And also there's communication issues between engineers and clinicians. And also there's a big gap of translating research from engineering to the biomedicine. That's how I started this biomedical study. And then afterwards, I studied a few different things, and obviously I was really interested in developing new biomedical devices and systems. And all of a sudden, my grandmother has an issue of atrial fibrillation and other heart-related stuff. So I think that's the moment that I decided to look into more about better systems and better sensors, because the things that she used were not great, obviously, and she has to frequently visit hospitals, and that's basically giving her discrete recording of those signals. So she's not really getting continuous real-time data recording so that she can recognize if something happens, right? She didn't have that before. So I guess that's the moment that I really dedicated into this field, that I have to develop better stuff for many patients who need new devices, new technologies.
Well, I'm so sorry to hear about your father, but kind of on behalf of everyone who has experienced some tragedy related to cardiovascular events in their family, and it being, the number one of the biggest health issues and mortality causes in the U.S. and around the world. It's incredible that you've been able to leverage it into making a real difference for everyone else, and so thank you for doing that. I'm a little bit interested to see, because the cardiovascular link makes sense, right? And with your grandma, that monitoring is all brilliant, and the application and population is very clearly defined. But from thumbing through some of your other research, the breadth of other applications of these biosensors are incredible. So would you maybe walk us through, after the cardiovascular recording and monitoring, after that, the development of that, how did you then get into muscle recording and control for people with, certain quadriplegia issues or any motor control issues? How did you make that jump?
Yeah, good question. I guess I got into those new research field because of my colleagues, right? We have, monthly basis or bi-weekly basis faculty meetings between engineering and medicine, and I'm part of that biomedical engineering. So we are frequently discussing something new research questions and problems that we have to address. And I saw a talk from one of those clinicians who mentioned about there's an issue of existing devices for measuring those good signals with people continuously, basically. So he tried to use multiple devices that are commercially available. However, he couldn't really get something that he wanted. So that's how I got into this muscle data recording system. So we wrote a proposal together, and we got funding. So that's how it started, to replace the existing system, or not just replacing, developing a new system that can give him better data, or data that he couldn't record it before. That's how I started to look at the muscle related devices. At the same time, I'm also studying other things like brain related signals, something about stress, human stress. And I think those researchers also have similar stories that I heard from other guys, clinicians, and my colleagues, that they brought those issues that, oh, you have that, I saw your article, I saw your heart monitor, that you can use new technologies to develop new systems. How about you can look at other things that still have problems, right? So that's how I got into those other research areas as well.
Right. Yeah, I mean, you designed a tool. You designed an entire new tool belt, and now everyone's going to be calling you for a consult about how do I address this specific issue.
Exactly. Yeah.
It's incredible. It's a pervasive technology, truly. One kind of specific question, bringing, I guess, my own little thing to you. One of my best family friends has Parkinson's, and so that's a specifically kind of it's an interesting consideration as far as how this technology could apply, because that leads to if you're recording the specific activity of muscle groups as opposed to maybe some kind of precognitive approach to muscle control. How do you handle people who have tremors or have some form of paralysis as maybe opposed to some amputation? How do you kind of address into those niches? What's the different tech?
Right, very good question. So one of my study that I published recently includes that new outcomes regarding Parkinson's. So as you mentioned that, Parkinson's disease is horrible because it can weaken your muscle strength and you're losing your control. So there's tremors and many other issues. So they have a lot of problems of controlling their bodies. They are relying on wheelchairs, right? And also, even that wheelchair cases, they have issues to control it because of their lack of motor controls. So we develop a new method that can measure brain signals, right? So our systems can not only measure other muscle-related activities, but also can measure the brain signals on the scalp. It's
really, on the scalp?
Wow.
Yeah,
Wow.
on the scalp. So it's completely non-invasive, meaning that
Right.
it's not penetrating your tissues, right? So you basically put the sensors over the scalp. It can be
Mhm.
non-hair-bearing regions like forehead or back of the neck or mastoid, but also it can be mounted over the hairs as well. But the good thing is that we don't need to penetrate the tissues, right? So it's very safe. However, there are existing devices that you can use for that brain signal recording. It's called electroencephalograms, right?
Right.
But it's following the pretty much same materials and device arrangement as I mentioned before, rigid
Right.
electronics. So that's why they had to put that rigid electronics over the hairs or soft tissues. It's even more challenging compared to other locations because of hairs, obviously,
Of course.
right? So you cannot have really good contact of that sensors to the skin. So basically they have to put a lot of gels on top of your hairs.
Yeah.
So you have
And
to
bald is a
shampoo
cool
your-
look, but it's not for everybody.
not for everybody, and you have to shampoo your hair every day or after that recording. So you cannot put that sensors for continuous data recording. That's impossible right now, right? So we found that our very small sensors, right, you have to shrink the size so they can sort of penetrate your hairs like a spider legs or something. So it's very deformable, so you can penetrate those hairs and then make a good contact to the skin on the scalp. Or you can put that very thin sensors and electronics over the forehead to record those brain signals. And the quality is pretty much the same as the conventional electronics. However, it's ultra thin, ultra light. At the same time, you can measure those data continuously. I think that's the major difference. So we can measure those brain signals, right, as I mentioned that. Then you can convert that signal to control those targets, like wheelchair or something else, for somebody who cannot really move their bodies, right, because of paralyzed limbs and Parkinson's disease and so on. But it's, as you can imagine, it's not really easy to pinpoint what's going on in your brain, right? because
course.
you are doing many different things based on that brain function. So we spend a lot of time to exactly specifically find out that signals related to something that we can control, external devices and others. So obviously it's ongoing research, and many people are still looking at this brain. That's what we are doing at the same time, but we are very hopeful, and we saw a lot of potential that we can expand this study further and further to provide better system platforms to record those brain signals.
Cool. Well, something that Mallory and I were talking a little bit about before you hopped on the call was the ability to maybe use both EEG-esque recordings and muscle recordings in concert in order to kind of have more coordinated movements. Because at least I think the golden standard of any kind of these technologies, any type of any artificial hand, any of these robotic techs that are coming out, is to be able to do kind of very natural feeling movements. So both planning for the location of that limb to move while also considering the opening and closing of different digits. So by having that kind of dual recording of both something maybe a bit more cognitive or precognitive and the actual muscles themselves, do you think that that's achievable?
Yeah, that's good question. I got that question from one of my colleagues like a few months ago. I think certainly people are looking into new things because, as you mentioned, that possibly muscle activity is not enough, or just cognitive recognition is not enough to offer that 100% control of that prosthetic devices and others. So that's possible. My answer is possible because our systems can measure those signals simultaneously. And we can use our data recorder, which can be wirelessly measure those data simultaneously, and we can merge those data together and analyze those data together. So we can find out I guess common signals or something that we can recognize simultaneously. Then I believe we can improve the existing systems that we have.
That's great. You got something to say, Mallory? You got a question?
Just, it really interesting to see what you think or where you think this field is going over the next 10, 20 years, what you'd like to see happen. And, like I mentioned, I come from a public health background. So I think a question that comes up for me is also just ethical considerations around these types of devices. So I'd love to hear how you reflect on that.
Yeah. Those are good questions. First of all, your first question about what's going to be happening in near future, right? 10 to 20 years. I believe we're still in the pandemic situation, right?
Right. We have to get through this first.
Exactly, right? I think this pandemic gave us a lot of lessons in many different areas. However, in terms of these medicine areas, I think we learned something that we have to move forward and try to give less burdens to the medical systems, because we are 100% relying on, that inpatient caring, right? We have to go to hospital and get those diagnoses and therapeutics and so on. So I'm thinking that once I can, or my colleagues, somebody who's in this field, can continuously develop this technology, then I think we can offer more about home-based diagnosis and others. I think it could give us definitely advantages in terms of medical cost reduction, and also saving doctors' time, and possibly use their time for more urgent or patients or some other cases, emergency cases, right? And for typical diagnosis can be easily done at home, right? By sending the device to home, right? We can definitely do that right now.
Yep.
And they can just put that device on the skin or somewhere else. Then it automatically measure the data and send the signal automatically to the doctor, right? Things like that. I think that's gonna be possible, I believe. Obviously, it's challenging to commercialize something, right? It's different from research. That's another topic that we have to discuss, obviously, because that requires money and of different things, right? Manufacturing capability and others. However, I believe that we are getting there, right? We are developing new technologies, and it can enable, that home-based medicine and other things possible. Not sure whether it's within 10 years, but possibly, within 20 years or something like that.
Mm-hmm.
For the ethical thing that you brought, I think that's really important question that needs to be discussed. I'm not an expert, I didn't study public health and others, but that's what I'm hearing from other guys, right? How you can handle those data safely, right? We are getting a lot of questions about those things because now we are getting more data with this device, and it's wireless, it can be breached, and data can be stolen by other hackers or something like that. And again, I'm not an expert, but I think as we are developing new technologies in terms of new ways of getting data, we have to also pay attention to these ethical issues and try to be very safe and thorough in terms of data security and others.
And I think I'll ask the question that might be on a lot of our minds, which is the clinical applications of this are incredible, and it's obviously what should be prioritized because it stands to bring the most good to the most people.
Right.
Absolutely. But beyond that, where does the line start that it's human improvement, and where does this discussion lead into kind of it's a bit lofty and it's a bit sci-fi and whatever, but the research that you're doing feels like we're on the precipice of moving towards real machine integration into humans. And I'm not going to be the one to say cyborg. I guess I am. I just said it, but but getting to that point, because I don't know. For me, it's exciting to think about my or any of our precognitive our precognitive thought processes, or some movements that we make truly controlling the technology around us, which kind of becomes limitless as to the integration. Do you think that's the right way to look at this technology? Do you think that could be a bit too anxiety inducing for people who may be a little bit less tech not savvy, because that's the thing, this would remove savviness. This is just you thinking about it and it would happen, but a bit more fearful towards tech integration into our lives, I'll say.
Yeah, I sort of thought about it because people sometimes ask me about their questions, right? What can we really do for other fields, not just biomedical devices? Honestly, at the moment, I don't work on any other those projects because that's not my top priority. However, as you mentioned that, I believe this technology can be used for something else. I just hope that, I don't want to make, I guess, killing soldiers or something like that, right? I hope it can be used in good ways that people get benefits out of it. But, obviously I'm not controlling those things. However, it's certainly possible, right? These devices now, not only just wearable, but also implantables, it can give you better signal recording, not just cognitive or something else as well. We are getting there. So in one day, I mean, in a near future, again, 10 to 20 years, we can see, new cyborg systems or new robots that's obviously moving based on your thoughts, your willingness, without putting anything, just looking at or thinking something. I think that's definitely possible, even though I'm not just working on those areas yet.
Yeah. Extremely cool. It's a lot to think about. I guess pulling back into the clinical world really quick. Could you maybe walk me through what the training process is like for this? So say you are fortunate enough to be a patient who is chosen to have such a kind of possibility of a life-altering treatment or technology integration. What is the process of training to use this look like?
Yeah, okay. So training of this device for those users, right? Yeah. Currently, we are doing those processes at the Emory hospitals right now with those clinicians who are dealing with those patients. We are trying to follow the conventional protocols as much as we can. We just replace the device from something that they used to ours. I'm not really controlling those training processes because that's not my area. So I'm relying on those people who have expertise, right? Obviously, there are many other things to be considered in terms of ethics and a few different things. So, yeah, currently, what I can tell you is that we are trying to follow the conventional gold standard protocols that they have. However, we tweak something so that instead of patients, just come to the hospital on a daily basis, we can send those devices to their homes so that they can measure the data that they need at home and send those data and see what happens, things like that. So we are in those transition period to see what happens with this new system.
Yeah, that makes sense. Watched a really cool video on your website about wheelchair control using eye motion. Could you tell us a little bit about that and what maybe the next step in that process would be? Because that seems to be able to do a ton of good for people.
Okay, yeah. Obviously, that if you're interested, you can definitely visit my website, listeners, and see what happens. It's not a patient. It's one of our graduate students who developed the technology with me. Right. We used two different things. We used eye motions, the one that you mentioned. That's something we can measure by putting sensors around the eyes. Again, it's non-invasive, just on the skin. Then, we can pick up those data because our eyes like magnets, so it's polarized. So we can easily pick up those DC direct current potentials when eyes are moved, like up and down or horizontally, things like that. So then we convert that signal to a command to control the wheelchair. That's one thing that we did. Obviously, we did the wheelchair control, but however, we also used that similar arrangement to control a drone, like RC car and flying drone, and even we tried to use that signal to have PowerPoint presentation, right? Instead of clicking.
Wow,
that's brilliant.
We use, that thing to control that presentation.
We'll have to integrate that into our podcast recording, Jazz.
Totally. If only we could train our mouths to say what we want to say.
Sure, we can do that, right? Or, there are many ways to do those things. We call it as human-machine interfaces, right? So we can use muscle activities. And recently, something that you asked me before, we use the brain signal, right? We use that specific brain area related to the eye so that we can capture what the user is trying to do. So we're basically predicting user's intention by recording the brain signals on the back side of the head where our visual cortex is. And we use those signals to control wheelchair as well. So, there are many ways to control those external devices as long as you are getting reliable signals from the human body.
I think we should also maybe talk a little bit about how this recording actually happens, because I think it's pretty understandable that we're working as huge circuits of electronics, and we have electrical, conduction going through nerves that are running from head to toe and everywhere in between, central nervous system processing, everything like that. It makes sense when you're doing maybe something more like electrophysiological, like patch clamp or anything of the like. But I think it's a little bit harder to grasp the concept that we have the ability to detect electrical signals on our skin. And I know that tech's been out for a little bit, but could you walk us through how that really works? I think it's pivotal for this research, but it's a hard thing to wrap your head around.
So in terms of trying to clarify, in terms of hardware or like the physiology standpoint?
I think a little bit of both. Yeah.
Okay. Yeah. So in terms of physiology standpoint, currently we are targeting non-invasive signals, as I mentioned, right? We are trying to put those sensors on the skin instead of under the skin to measure those data. As you mentioned, we have tons of nerves. They are spraying out to the body, and when we are targeting brain, we are targeting heart and others muscles. Those cells are communicating through electrical signals, and obviously, brain sending signal through the nerves to move something like muscles. Heart is obviously operating by itself. However, when heart is pumping in those things, there are generated electrical signals. So, whatever you're doing, even during your sleep, right? there's electrical signals happening, right? We can measure those signals on the body, on the skin. Okay, there's always something's going on. Obviously, your brain is not 100% turned off during your sleep. It's less functional. However, there's something's going on as well. So you can measure brain signals during sleep as well to see what happens, whether this guy is having good sleep or not. Very similar things that we can measure. Those similar electrical signals. I'm not gonna go details about how we could really target those signals in terms of in-depth physiology, but simply speaking, right? Anything that we do, thinking or moving, and they can generate those signals. Another example that I can tell you is about stress, right? When you get stressed, everybody gets stressed, then you see that we have the emotional arousal, right? Then that sort of works with your body system, that your blood is kind of accumulated throughout your peripheral nerves area, so that our skin conductance is changing immediately, depending on obviously the amount of stress that you are getting. So that's another example that it's not electrical signals, it's more about natural skin conductance change, the electrical properties of the skin change. So we can measure that conductance change to see what happens in terms of the numbers, whether you are getting severe stress or mild stress, things like that. So that's another thing that we can measure too. In terms of electronic devices, sensors and circuits, yes, we need state-of-the-art systems to get really good signals. And typically, I don't know whether if you visit hospital, if you ever visit hospitals and measure something about heart signals or brain signals that I mentioned today, then you immediately see that there's huge devices, sensors connected through wires to the tabletop systems or something. We develop new way to shrink everything down further and further, so we can miniaturize it. So now it's a little bit smaller than a single credit card, depending on targeted sensing signals and number of channels. However, typically our device is less than let's say 3 centimeters times 4 centimeters in terms of footprint, the area coverage. We borrow those new technology development ideas, right? So that we can have densely packed circuit components, and we stack them together. So instead of spreading out, we manufacture the device in a multiple layers, right? Having sandwiches with turkey, ham, and so on. So and we press them together and squeeze them together so that the overall form factor is very small, so that it cannot really bother you. So now, and as I mentioned, that we need sensors as well. We need sensors and circuits together, but those wires are not, ideal, because wires can cause artifacts, signal artifacts, motion artifacts, and also it can be tangled together. So we embed these sensors again together with the circuits, multiple layers. So we put sensors at the bottom so that you can have a good contact to the skin. At the same time, you have circuits on top of it so that it can process the data. And all of those devices that I mentioned today are wireless. So we can use a conventional Bluetooth system that we have, and you use on a daily basis. You have that Bluetooth on your smartphone, right? So you can connect with AirPods or anything like that. We can use that Bluetooth, or we can use Wi-Fi, or we can use RFID. I don't know whether RFID is something that you use the entry card or something to enter the door, right? You need the proximity contact. That's called radio frequency identification method. So we can use that one as well. So there are many different ways to use this wireless system design. However, the key point is to make it densely packed, multi-layered, squeezed manufacturing of those sensors and electronics.
Well, it's incredible.
You're certainly packing a lot of technology and potential into a really tiny, tiny space. So That's
Yeah, we are trying
really
to make it
amazing.
like even smaller than a quarter, but it's not possible.
Right.
So,
I mean, did you just kind of coming from a mechanical engineering background, were you just drawn to this because it's engineering to the max, I guess, nano degree. It's as hard as it gets on the smallest possible scale. I mean, I work in my lab does nano engineering for nanoparticles, and that's a bit of a different scale, but a way different application too. Those are injectables. But for you, yeah, I mean, this must just be the coolest thing.
yeah.
Such a challenge.
Yeah, I'm not sure how much you know about mechanical engineering, but mechanical engineering is very broad. Right? It includes multiple areas of study, and one of them is about manufacturing, right? And traditionally we manufacture big stuff, obviously. However, as you talk about, many biologists or many biomedicine people use nanotechnology, right, to have gene therapy and other molecular manipulation or something.
Right.
But I brought that similar idea for manufacturing. So we do nanotechnology-based manufacturing, nano-manufacturing. That's what we call it.
Right.
So we play with particles instead of molecules. We play with those nanoparticles to make sensors instead of huge scale printing, right? So we use that. We can do like very small nanometer thick layer with new manufacturing technologies. Obviously, I can talk about the manufacturing more than an hour, but I cannot do that right now. But, obviously, so while technology is developing, manufacturing technologies are also developing. So now we can print very small particles. We can build ultra-thin sensors. And also we have packaging technologies in a way that we can stack multiple materials together and connect them together without using external wires. Right, it's all connected by internal connectors, nano and micro scale technology.
Well, it's unbelievable. Dr. Yeo, thank you so much for joining us today. Mallory, do you have any other final thoughts or questions? I feel like this is a unique opportunity to get to speak with someone who's so at the cutting edge, so at the forefront of technologies that I'm sure will be so pervasive in our life going forward.
It really is. We're so exciting to see all of these different areas coming together. I think one, reflection I have in talking to you is just the beauty of collaboration in science, from engineering and medicine to ethical considerations to the manufacturing and distribution and implementation of new technologies. So it's just really amazing to cover so much ground in just this one conversation. So I'm grateful that you're doing this work and willing to share some time and insight with us. Thank you so much.
Thank you. Thanks for having me again. Before wrapping up, I just wanted to thank my group members, my students, my postdocs, and my collaborators, right? They are the ones who made everything possible. I'm just writing something, getting money in to help them. But they are doing those hard work day in and day out, right? So I'm really thankful for them. And I think, they can change the world eventually. So, I'm really hopeful for my students and postdocs. They are bright, they are diligent, and they have a lot of enthusiasm to make better systems for, people who need their help.
It's wonderful. Thank you very much, Dr. Yeo.
Thank you, appreciate it.
Absolutely. Well, and with that, that's the end of this episode of Imagination. Thank you so much for joining us, and a huge thanks to Dr. Yeo, but also a massive thanks to Mallory as well. It's great to have you here, and you provided some incredible insights as well.
Thank you, Jazz. You're the mastermind behind this, and it's a pleasure to join. So.
Oh, yeah. So, as always, I'm Jazz Munitz.
And I'm Mallory Stellato.
There we go. Thank you for joining Imagination. Talk to you guys soon.
Bye.